So guys, first we open the Mix. In the Mix, we need to upload the DICOM image. Click on the new. And here is a DICOM image of our aneurysm case 1. First we select first one and go down to the end one. And with the end, press the shift and click and just click on the next button. So it will import the DICOM image. So you can see that our image is okay. Then just open. So here is the Mix open. I need to show different views. Go to the views layout and select the different. So this one is X-rays and another one is axial and coronal. From here I will use another layout vertical, so you can see axial, coronal and sagittal views. Now I make a little bit increase the size and go for the threshold system. So segmentation and threshold. So the threshold, you need to select minimum value and maximum values. If you select the adjacent, if you need more small, then you can increase the minimum value. And if you want to see it's a 0, so you can see also. If you increase, you can get the small as a big vessel only. So the minimum value I select around 11,000, sorry, 1,100, because my focus is only large artery. And the maximum value, if you see, if I decrease it, the inner of the arteries, you can see there's a white, right? So missing it. So I try to make it more. So okay, now you can see here the green, and go left click and calculate the part. And there is a different low, medium, high and optimal quality. So you can select which one you want, but I mostly select as optimal and go for the calculate. So it's take a little bit time according to the geometry. So from here you can see the green is keyed already STL file. Sorry, 3D reconstruction. But okay, I need to change the view and show different layout so you can see in the big one. So here is our geometry that we keyed from the DICOM image, and you can see very small pieces. So we need to go down and left click and go into split, and there is an option for all large part, large part or two large part. So because you can see there is a two large part, one is this one and second is this one, so we will select the two large part. If we select just one large part, maybe we miss our main artery. So two large part and select. So you can see the small pieces are disappear and there is a two larger. So our main target is this intracranial artery. So we will delete the another one. So you can see this is our aneurysm, and our main target is this aneurysm. So left click and we go for the smoothing. So you can see different smoothing, like you can increase different iteration 0.5, sorry, it's a 5. You can see it's very smooth before it's comparing. So you can select different smoothing factor 5. Now we will select 3. So you can see very small difference. And if you try to smooth iteration like a 15, yeah, if you make a more iteration, the text will be shrink. So I just want more original artery. So I try to minimum smoothness. So I will select 3. So this is our geometry. You can see it's more smooth. So now we're going to export this into the STL file. Click in export, and on the desktop we save our test tube. So here we can name as a STL file, STL from the Mimix, Mimix, and save. So our STL file is saved. So we're going to close it and open the space clamp. So our Mimix as is complete. Now its space clamp is open. So we need to upload our STL file here. So from here, go to the desktop, test 2, and from here you see it select all files, so you can see STL and open. So you can see this is our STL file that we generated in the Mimix. So now and you can see in the different angles, and our main, this artery is our target because we need to simulate this one, but other are parts are the extra, these areas are extra parts, so we need to delete it. So for that we need to go selection, and from the down we select the paint, and paint you can see we will cut it from here because our main target is the aneurysm area, so we will cut from this part. Just right click and delete. Okay, so after delete you can go to the facet and select the separate all. You can see big one, so click and delete this one. Yeah, so our from here in these two also we will going to cut these two big branches. Yeah, so select and delete, go select and make it separate. And this one is also from, because our target is only aneurysm, so we not need all this area, so we just delete it and go to the separate all and select and delete. So still there is some arteries we not need this one before, it's before the aneurysm, so we'll delete this part also, and this part also we're going to delete. So when you're doing this one, you try to make the arc like a more arc, so it will looks more smooth. So we will try to make it more properly, like clearly. Yeah, so now it's a delete, and now we're going to separate again. That's, I think it's not touching here. Yeah, so we're going to the separate and delete it. So here you can see, I think it's a good cut. So if there is a speak, then it's maybe cut difficult for the making. So there is a two thing. One is a cap and one is a page. If we select the page, you can see this is so flat. It look like not realistic. So we need to make, when doing side things, it's page. Now you can see it's very clear. But on the outlet or inlet surface, that is the opening or the closing. So better you can try to make it more regular than make the cap on here. So now this is the outlet one, so we will select here and select the cap, and you can see it's a flat. Yeah, but it's not regular because we need to do it later. Outlet and inlet smooth, we will do it later. So so from here we need to delete this small extra arteries also, so we will select it and just click and delete, separate it, and just delete this part. And this also we need to delete, so try to make it more smooth, so it's when you're making the pages, it's not overlapping or anything which may cause our simulation error. And try to cut as possible as the small area, so it's make good. You can see it's very look more smooth. So we will cut all the small pieces. Yeah, separate, delete. So because it's one side is little bit upward, so I just need to make it smooth, so delete and try best to make it more smooth geometry. Now it's smooth. So other part we just need to delete all these one. If you see this one is the most difficult, because it's very small and very difficult to see it, so we need to careful about this one. So you can see this big, and so we delete this one and go for the separate and click on the delete and delete. So if you see this kind of things, it's look normal, but if you see in another angle, there is a big hole. So we need to delete these things also from the geometry. Separate, facet, and delete. Now we use the page all of this to make it more smooth. Yeah, if you see this one, it's also there is a big damp hole inside. So for that we need to repair this one also. So we just circular and delete this portion and make it smooth also patch. Yeah, so we do all the finalize. This is our smooth one, but still the mesh is not that much smooth. So far you see outlet and inlet is not smooth. Now we're going for the smooth, and there is a flattened peaks. If some like you see this one is a very peak, so it's make a flatten and edit facet and volume away. But I do the edit facet because it's increase the facet size, increase the facet numbers, and it's more smooth. So I do one smooth, so you can see how it looks very beautiful and very smooth. Yeah, now it's time to outlet and inlet making smooth because it's irregular. So for that we go into the design and select the cylinder and click on the center and make a one line and make a one tube. Big tube as big as good, and moving to the pool and select the pool, and we can see it's cutting proper plan or not, like it should be like a smooth cutting. So when in this one I'm confident of this, so I go to the facet and subtract. So I click on the my main body and then click the new tube that we make. So you can see this make a very smooth inlet surface. The same process we're going to do with the outlet. Go to the design, cylinder, click on the center, take a line, and make it a little big, and with the pull, click and stretch. And same thing we can do with another outlet area. Click on the center, change the angle, make the line, and make the tube. Yeah, so then need to pull this one and pull another one also a little bit high, but this one looks good. So the another outlet one, you can see this one is not straight, so we use the move, click on the surface and little bit rotate and adjust, so you can see it looks more better, little bit more. Yeah, so you can see, but if you see there's a notice there is a one peak, maybe it's make us difficult, so maybe we can do little bit more cut, or so it's not effect on the surface. So yeah, so adjust and now go to the S2. So go to the facet, subtraction, click on more model, click on the new tube. It will subtract that one. After finishing subtracting mesh, we do another one. So it's so it's ready now. So you can see the outlet is also very smooth. So now we need to save it. So we make a 3 files here. Save mimics first, because if we need to work again on this stage, we will use that file, and second we will save as a STL file. Yeah, so change the name STL smooth. Sorry, I make a mistake there. STL smooth, and just save it. Yeah, now our next step is the ICEM. Open the ICEM and close the space clamp. So now in the ICEM, we need to, most important is the setting, and go to the size. So we will select the model and unit and select the millimeter and apply. And second is the memory. Go to the setting and the memory and make it almost everyone is same, like 4096, and apply. Okay, so now we need to import our geometry. Go to the new project, open the project, and go to the imported model, imported geometry, facet, and SDL. Desktop text file, smoothing, open. So done. So the geometry is okay. Click on geometry, surface, and select the solid simple display. So this is our geometry that we make in the sim. So now it's a repairing geometry. Click here, tolerance. You can select the different value. I select mostly 0.3 or 4 and apply. So it will generate the border on the extended and indented tube. So this is also if there any mistake or anything that we need to repair, it will show the if there any error they show in this one. So next step is created the part. First one we created inlet surface. Write inlet surface and give it and select this inlet surface and click on the middle button. So it's create the middle. So if you remove model, you can see this surface we just created. So there is a 2 outlet, so we need to create it also. Outlet 1, outlet 1 OUTI 1, and select the outlet 1, click, and second is outlet 2 or 2, and select the part and click the middle button, so it's created the outlet 2. So now it's time to make the extended tube. How to make the extended tube measure we will teach you in another video, but here we will just make how to create extended tube. So first of all we select there and go select 3 points. Select the one this area 1, 2, and 3. See, we make a 1 point in the center. Then we need to make a coordinates, local coordinate system, in which you click one. First click on this click on the center 1, 2. So press the middle button. Oh sorry, I click outside, so I need to delete this one again. Delete, and again need to create it 1, 2, and 3. So you can see it's make the coordinate of x, y, z. So the y location is the location direction where we need to make our extended tube. So go to this click here and XYZ point, and you select. You can add your length of the extended tube. It's according to the resistance that we measure. So you can see this point. So now click. Yeah, if you want to remove this coordinate system or not, it's okay. I will remove so I can see the main point. Click here, and here you make up one line. After that line, you click here and tube. So we need to give the name inlet tube. And first we need to click on the line, then click on the there. So it's happened. Now it's time to make the inlet surface. So surface, and we just give the name as inlet. So click on the line and done. Middle finger. Oh, you see this is a red square. It's a big mistake. Where is the mistake? If we zoom this area, so there is a small part also and we miss it. So we need to more focus and see it. If it's become the surface became right, so we will delete and we start again. Click the tube, click on the middle line. Now we need to zoom it. Click the baseline and click that small line, and okay. Now this is we created our inlet tube. Now it's time to make the inlet surface or inlet. Oh, sorry, we forget to change the inlet as inlet tube. So, okay, inlet 1, and we rename it. Left click and change the name. Oh, sorry. So inlet, yeah, inlet. No, inlet tube. Sorry, inlet tube. Because before we mistake. So now it's inlet, no inlet. Oh, sorry, D inlet. Oh, now click on the big circle and zoom it and small one and click. So it's make the inlet surface. So second, we going to make the outlet. So for that we need to do same process that we do for the inlet. So first, because we need to use the reference of one, if there is a two outlet only, then one is used as a reference, and second we extend it to two. So same process, 1 2 3, make a middle line and make the coordinate system, go 1 2 3, and click the middle button. It will tell us now on the go and XYZ. Okay, just example is 20 mm, so apply. So you can see we get our point from 20 meter away, 20 millimeters. Go make the line, click here and tap, make a line. And now it's time to make the tube inlet. So it's an outlet tube, because we have only one outlet, so we say outlet tube. If two, then outlet one or outlet two. Click on the line, 1 and 2, middle button. Okay, make it 2. Now it's time to make the outlet surface. So click on the surface area, change the tube to outlet. So because we have only outlet, but we just select 1 and 2 outlet. So we already, sorry, that's mistake. Okay, so middle, okay, so this is we make a already extended tube. Now it's so now it's time to make the body or material inside. So we using the blade. Blade is a fluid, so we tap the fluid, click here, and zoom the inlet area. First click, second click, middle button. Now if you remove the inlet tube, you can see the fluid inside. So we need to if we have three body, we need to make this in all three bodies. 1 2, click, and if you remove the wall, you say wait. Now it's time to make in the extended outlet tube. Same process, we can do the 1 2, down, okay, 2, click, yes. So fluid is ready. Yeah, so we just delete the geom file and delete it. Delete it. Yeah, so now our geometry is ready. For so going to the save desktop test tube and new folder, which will be the tube. We make another folder as a mesh, and next one is the CFX. Done. So why we making this different folder? If we have problem in any stage, we use that stage file. So first save in the tube, and now in the mesh. So it's ready. Now it's time to meshing. Click on the mesh button and click first one, and here you can select the different mesh size. So mostly we're selecting 0.3 because we already have different mesh integrated mesh independent test. So we select 3 is more good for simulation term, and the minimum size is 0.2, and apply. Click on prism meshing parameters, and this one you will need to measure it on the formula. I will teach you later, and mostly it's 0.05, some values, and the triangular quality is left apply. And now it's you select here robust artery, because later we're going to do the quick delineate, but now first one doing the mesh is robust artery and apply. Now it's going to make a prism layers on the tube, wall, and inlet tube. Because our focus is only our body, so we not need to see any simulation in the extended tube. So we make the extended tube size, mesh size is big, like a 0.7, because it's not our target. Apply and dismiss. Now now it's time to run. our simulation. So confirm transformation robust, and we need to click the create mesh. Now compute taking time almost, it's depend on the mesh size. So now the compute is finished because I just skip the mesh timing. So you can see, zoom it and see the mesh quality. It's very small and you can see the three layers. I need to change the color because I think you not see it clearly. So change the color. You can select different color. Like yeah, here you can see three prism layers and the internal mesh, triangular meshing. Now we need to the edit mesh. First one is smooth mesh globally. Click here. So here you can select different smoothing iterations. So let's see, 5 you can see, and now we will select 3. Oh, sorry, it's 0.2. Sorry, is 2. Apply. So it's take little time. I need to skip it. Yeah. Okay. So we change the iteration again with 5. Okay. Let's apply. Yeah, so now it's going to the check meshing. Click here and no need to change the setting, just apply. It will take a few minutes, and so it's complete. There is a no problem was found or duplicate element. So now, so quality matrix iteration unconnected verticals are okay. So now go to the mesh again, and we need to do delineate meshing. So click here, from robot to quick delineate, which increase the smoothing or quality. Go and computing here and unselect the create mesh prism layer. So compute. Yeah, so now the mesh compute is lit. Again we go to the edit mesh and smoothing. You can see the quality of the mesh is already changed. Now it's increased the mesh quality. Now going to the check again, apply. Now deleted the unconnected vertex. Yes, so there is a 97 unconnected vertices deleted. So okay, now the mesh is complete. So we check the mesh information. So it's about 2.2 million mesh in total number of elements. So before go to the out mesh, we're going to save it. Yeah, so we just save to mesh because I confirm that it's in the mesh folder. Click here and it's now use the output solver. If you are doing the Fluent, use just ANSYS Fluent, and if you are simulation is in the CFX, select CFX and go down and apply. Solver ANSYS CFX support unstructured meshes. Then now it's going to the output you want to save because we just save it, so no need, just click no. And from here I need to save in the CFX folder, so I will write CFX and done. So done with transaction, but before close it I want to check it, confirm there is a my folder is in there or not. So go to the desktop, test file to and CFX. Yeah, so this is okay. So minimized and sorry, I don't know, closed it and select no project. Now it's time to open the CFX. Tap CFX, open it. Yeah, now first click on the pre CFX pre. Now click on the new general. Okay. Now first we need to import the mesh. Go here, desktop, test 2, CFX project, open. Okay, here is our STL file is here. So first of all we need to do expression for the inlet because we're using the pulsatile flow. So we created our expression from this waveform is from our one of the literature review. They're using this waveform, so we make the expression from this waveform. That is, we work in the MATLAB, so in next video we will teach that one. Here this is the expression that we make. We use the Fourier curve fit, Fourier 8, and copy and go and paste here and apply. So our expression is written now. Now it's our material. There is a air ideal case, air, aluminum, copper, salt, but there is no blood because we're working on the blood. Click edit in the command editor, and here we also already write the properties of the blood, like dynamic viscosity, density, molar mass. So just Control plus all and copy it and paste here. Select and paste here and process. So our material is okay. So you can see the blood. Okay, apply. Close it, and now go into the analyze type because we're doing pulsatile flow. So we select the transient. Click, and we total time we are using the 3 second, and the time step 0.001. So you can select time step according to your simulation. So you can see here analyze flow, analyze domain, default, and output control. For going default, because we're using the plate, select plate here, then fluid properties because it's plate, so none, option turbulence, non-laminar, and analyzing we need to set this 0 boundary condition, starting boundary condition, so all is 0, and check the unit centimeter per second, apply. So you see one is disappeared. Now it's trying to create it up parts. First we create the inlet surface, so go and write inlet from where the plate is enter in our geometry. Type inlet. Okay, so the boundary is inlet, and from here we select the inlet. You can see not inlet tube, here is an inlet, and select the inlet, open. Okay, so now boundary detail, because we use a pulsatile, we use our expression that we saved before. Click expression and apply. Okay, now is created to the outlet. We have two outlets, so outlet 1, then press OK. Outlet is the opening, so we can select outlet first. You can see the outlet, and OK, and go to the boundary detail. We writing the relative pressure, so 93.3333 into the mmH, and how we get this value is a systolic pressure over 3 and multiply plus 2 multiplied by diastolic pressure over 3. So we will get the relative pressure. So each patient has a different relative pressure. So we use that one. It's 93.33. It's like a normal patient one. So okay, so this one. Now another one is we get outlet 2. Same process, it's the opening, so we will select second outlet to surface, so that will be our outlet because we don't have a extended tube there. So 93.3333 into mmHg, so apply. Okay, so still we have inlet tube and outlet tube. So far we need to give them as a wall properties. So inlet tube, click here, and that is the wall, and select the inlet tube. You can see there, and okay, so create an outlet tube. So outlet, because we have only one outlet tube, so we just outlet one tube. Select the wall and outlet tube. Okay, so default domain width, because this is our wall, so we just give name as a wall. Save it, and now it's going to check. If you remove the wall, you can see this is our main geometry, and inlet tube, outlet tube, inlet tube, you can see it. Now it's solution units, and click and check the units. It's okay, click on that. Okay, no need to change any units, and go to the solver, and maximum coefficient loop we select the 50. As high like 100 is better, but it's take more simulation time. Now transist result, first one we use the select variable, and we need to select which parameters we need. So wall shear stress, velocity, vorticity, total pressure, velocity, pressure, and density, dynamic viscosity, and absolute pressure. We select OK. If you want the current number and others parameters, you can select, but it's to increase your simulation time, and so you need to select what parameter you need it. Okay, so from here, time list, because we have a pulsatile flow, we select this time list and copy. From here, we started from 1 to 2.22, so we're going to paste here, and now it's time to transact statistics too. So from here we will select first is a average, like arithmetic average. Click here. Pressure, we select on pressure, dynamic viscosity, density, absolute. So we will select all three, and OK. We need to select the specific that we need. Now it's we select the minimum, and same all the parameters that we select before: pressure, density, viscosity, absolute pressure, and also now it's time to maximum one. So we will select the maximum, the same parameters that we select in our first one. Okay, so it's our, if you want more like a standard deviation, root square, square, or full, we can do that, but we just need these three: average, minimum, and maximum. Okay, so our simulation is ready for the simulation. So you can see this icon. I need to make it small. Yeah, so click on the icon here, and where you want to run our simulation, go to the desktop, test2 CFX. I want to run here simulation, and you can give the name anything like case 1 or test2. Okay, run. So now it's depend on you. You want to run as a serial, or you want in local parallel. So for simulation first, we use a parallel, and it's depend on the computer. If you have 64 RAM, then you can select 8. So in the same ratio, in this computer, we're going to select the 16 and start simulation. Yeah, now this is the start simulation, and it's going to be take around 1 day. So yeah, it start running. It's take at least 1 day. So after running simulation, you get this file. You can see there is around 504 items, and also you can get the case file result and case one out. If we open the case one out, here is you can see the detail of the simulation. Like if you go down, and you can see the total number of the elements, like yeah, so total like elements, you can see 99.6 million of total number of elements, and 7.1 is tetrahedrals, and 2.5 billion are the prism layers, and total number of faces. And if you go down, you can see the simulation time and current number also. Like our current number is 0.2 here. Yeah, current number is at 0.2. So you can see the all details of your simulation, in which current number, Reynolds number, simulation time, everything you can see here. Okay, we need to close it and go for the post processing. Okay, okay, close it. Now you guess result and open the result, ANSYS post processing. So there is a geometry. If you want, you see, like the wall. This is our geometry wall. Because this is one I already run my cases before, so I just showing that one. So in which I have out 4 outlet. So post processing, click on the wall. There is a cons. So like mostly things we can see on the wall, like a pressure. So first we check on the wall shear stress. Apply, and the global we just apply. You see this is a BGR color, and so we mostly use the rainbow 6 because this color is a good color. So after that we also use the ranges, low colors, user specific. So mostly we use a user specific like a 30, so just a 30 or 40. Okay, apply. So this is at the 30, so you can see the minimum is 0 and maximum is 4. So beside that, you see this number is so big, so we make it a scientific, go to the default legend, and from here you can also change the variables or your specific. For example, I go to the user specific and like the legends as a WSS, which means wall shear stress. So you can see that one, and appearance we're going to the select as a fixed number. If you apply, you can see the fixed number, but still 00 is so we can see the precision also. So you can see you can do changes from here. Yeah, so if you want to see at different time steps, so for example at the peak systolic, which is around 1.18, so this is the peak velocity. When it's reached, you can see what changes are there. And if you go on the first one, first velocity, and at the full time one, full time, so you can see at different time steps. And okay, close it. This is a wall shear stress. So if you want to see other like a wall shear vorticity, velocity, pressure gradient, you can select different parameters here. For example, vorticity we can select, and because it's a global, because we not fix, this is the vorticity. If you want to measure another thing, for example, time average wall shear stress, so we need to write the expression like a wall shear stress into time average. So apply in the expression, go to the variable and click new folder and DASS and expression, select the TOS and apply. So TOS is we get there. Now we can see user defined TOS and apply. So, yeah, so here is the one TOS. So local user specific, make it 40 or 30. Okay, let apply. Yeah, so default because we write there is a wall shear stress. Okay, this is TOS, so you can make the TOS there, and also if you make the variable, so that's automatically set what variable you are using. Now we write other expression like OSI. In small we write a OSI, then click so 0.5 into bracket 1 minus into absolute into wall shear stress minus, sorry, wall shear minus a TOS bracket under divided wall shear stress, wall shear plus TOS. Close the brackets and apply, and go to the variable and new and see OSI. Okay, and select the OSI, apply. Now we're going to the RRT, same RRT in a small, then write a formula 0.5 into 1 minus OSI multiplied by TOS. TOS, apply. So variable, we're going to write a RRT. Okay, is right, and go RRT, apply. So now we can variable from here. You can you can select different like a OSI. So you see space. So SI is very low because we're using specific local 5 user specific. So you can select this one, and also going for the select RRT and see like that. So different parameters you can select. So pressure gradients, click and use global. So different parameter can you can select from here. Now if you want to see the velocity, we need to select the wall because the velocity inside the tube and not we cannot see on the wall, so we need to make it transparent and the color change. So now it's a transparent form. Now we go into the streamline 1. Okay, so domain starting from the inlet, and number of the points, let's start 150 and go down, and velocity because the flow is back or forward, so we use backward forward, and the color change to uh, prism rainbow 6, apply. So it's take little bit time. Mm, so a little bit wait. Okay, here is the streamline. So it's starting from the inlet and going to outlet, and one you can see there's a no flow because that is our reference outlet, and you can see inside the aneurysm. And we can also increase the number of the points. Let's make it 250, so the streamlines number is increased inside. Yeah. So if you want to see at different time steps like here, so you can do, but in the time steps uh, it's taking time for the streamline because it show created 250 at different, you can see here. So if you want to make it animated, you can select here and you can select time steps and specific like a 20,000 to 30,000, so you can select different time steps, and also you can save at your desired location. So I will show you, then just click here, it's a start creating the animated uh, animation of your flow. Like here is you can see my animation in which I use different uh, animated in 10 cardiac cycle in 8 seconds, and also the 1 cardiac cycle, which you can see here is a velocity, pressure, wall shear stress, vorticity, and pressure gradient. So you can make animated like this, in which you can see 10 cardiac cycle in 8 seconds. That is the realistic one, and we also 1 cardiac cycle in 10 seconds, like a cardiac cycle in 10 seconds, slow for the clarity how it's changing with the time. Yeah. So go again on the wall and select, let's see, wall shear stress. Okay, apply. Okay, so we need to change the transparent to 0 and see full form. And if you want to measure at a specific point, you can make the point here, and from here you can select any kind of a unit. So I wall shear stress, so you can select wall shear stress at different location, and you can get the result also, like if you want at different position, so you can use this one point for the wall shear. Yeah, zoom it and you can see. So close it, and if you want to save the images, go for the save image and select the location where you want to save. For example, okay, just save it here. Okay, I try to save on the desktop. Go. Okay, let's I think let's save in the documents. Save here. Save. Okay, and if you want to this area as a white, you can use that also, and transparent, but I prefer to transparent. And use screen, I will always select the 80K, which because it's the best quality for save. And if you see, I zoom this area, so the picture will be only this area. Let's go to the documents, use make it large icons, you see here. So you see this is the image that we created from this one, and it's only those area which is on the screen. And why I make that transparent, for example, if I want to make a open hair, let's go to the hair and paste in the space, so you have a very clear picture here. So any background you can use this picture, and increasing size, small or big, so it's not affected by the background. Therefore I select the transparent. Yeah, and if you want to see as a specific location, like if you want to see the dome of the aneurysm or anything, you can do that. And key for that you need to constant and change, make it again transparent. And let's apply. So this is the space, and I have already the in space claim I make the part of the dome. Here see, you see, and we can upload here. Oh, sorry, we need to go to the file. Sorry, go to the file, click on the import, and import surface line or point. So go select. It's case one. Sorry, see, aneurysm, aneurysm, data, new resistant case one. So we need to make all files, and you can see here dome. So we can select the dome and select the millimeter. Okay, so you can see here the dome of the aneurysm. So from here you can select the dome, and you select, go to the dome and color and make it variable. And if you want to see the wall shear stress, so select global and 40. Okay, and go to the color, rainbow 6, apply. So you can also see the specific location of the dome. So if you want to see any area or slice, you can make a slices in space clamp, and you can see specific location. So it's end. Hope you it's end of the video.